In section 4.2, we're going to discuss related rates. We're going to look at how two quantities are related and how changes in one quantity can change the other. A classical example of this is how the radius of the circle is related to the area of the circle. Notice that area is equal to pi times radius squared in a circle. So how does changing the radius affect the rate of changing the area? So the rate at which the radius changes affects the rate at which the area changes. If the radius is changing, increasing, then the area is increasing by however the radius is changing squared, right? That's what we think. So if you increase the radius and double it, well, then the area would quadruple. So if you double the radius, because the radius is squared, doubling is multiplying by 2. 2 squared becomes 4. Now, it's not quite as easy as just looking at the formula. In fact, if we want to look at the rate of change of the radius, not just how much the radius changes, but at what rate the radius is changing, and compare it to what rate the area is changing, then we need to use derivatives. We start by taking a derivative of both sides of this equation with respect to a variable like time, because a rate of change is something changing over a certain period of time. We think of both variables as being functions, just like we did with implicit differentiation. If a equals pi r squared, the derivative of this variable with respect to time, I can write as dA over dt. The derivative here, because our r is an inside function, we're going to take the 2 out front, 2r, and then multiply it times the derivative of r with respect to t. So we get the area is changing with respect to time, and the radius is changing with respect to time over there. Notice the difference here is, or the relationship here is that the rate of change of the area is equal to 2 pi r times the rate of change of the radius. So the radius and the area are linked, in this way, but their rates of change are linked in this way. And this should make sense, because if you increase the radius by 1 of a really big circle, that increases the area by a lot. But if it's a really small circle, increasing the radius only increases the circle by a little. Let me explain that with a graph. We're looking at a circle here of radius 1. Think about how if I increase the radius and start increasing the radius by, let's say, a number 1. So we go from 1 to 2. Notice that the area that I've added is the area inside this circle. So even though I've increased it by 1, I've added this much area. Well, if I would have started with a bigger circle, let's say a circle of radius 7, and then increased it to a circle of radius 8, I would have added a lot more area because this, even though it's the same width that I've increased, the amount that I've increased it by is a much, much longer amount. Or I should say the length here of this interior part is much, much longer than it would have been if I would have increased by 1. So even though I've increased the radius by 1 in each case, this adds a lot more area to the bigger circle than it did to the smaller circle. That's what I'm trying to say. And that shows that the change in area depends on what radius you're at right now. So let's do a calculation. Let's ask ourselves, how fast is the area of a circle changing if the radius is 15 centimeters? So the initial radius of the circle is 15 centimeters. And the radius is growing at 2 centimeters per hour. So we want to find the rate of change. Now, remember, the rate of change is this derivative. Derivative of A with respect to t is the rate of change of the area with respect to time. So the rate of change is, in fact, the dA over dt. We know that is pi times 2 times my radius times my rate of change of my radius. So the radius's rate of change is derivative of r with respect to t. In our case, we said the radius is 15 and the rate of change is 2 centimeters per hour. That means the rate of change of the area is going to be 60 times pi, or if you wanted to give an approximate and round that number to a few decimal places, about 188.50 is your rate of change. Now, if you think about the label on this, the rate of change of the area with respect to time, this pi and this 2 were constant numbers. The 15 was actually in centimeters, and the 2 was in centimeters per hour. That's always kind of a good indicator we're talking about rates, is we have a fractional type label. dr over dt is a centimeter per hour. So notice what's going to happen. If I treat that like a fraction, centimeters per hour, and I'm multiplying them by centimeters, the rate of change of the area is centimeters squared per hour. Does that make sense? Centimeters times centimeters, and then dividing by hour. So sometimes people will write that this way so we can see the fraction. Centimeters times centimeters per hour becomes centimeters squared per hour. Centimeters times centimeters, and then hour. There's no denominator here other than an implied 1. So 1 hour. So if we're talking about labels, we're talking about the area is increasing at a rate of square centimeters per hour, which is 188.50. And that should make sense because an area is measured in square centimeters, and the time is an hour in this case. Let's do another example. Let's take example 1 here. Try to follow along. Water streams out of a faucet at a rate of 2 cubic inches per second onto a flat surface, forming a circular puddle which is 1/8 of an inch deep. So pretend that there's a spigot outside and it's just going, and we have these parameters. The question is, at what rate is the area of the puddle growing? At what rate is the radius of the puddle growing? Let's do this initially, so when the spigot is just turned on, and let's do this after the puddle has a radius of 10 inches. So at what rate is the area growing? At what rate is the radius growing? This problem is going to force us to know a lot of formulas about what's happening here. The fact that this is a circular puddle, which is 1/8 of an inch deep, is really important. The fact that we're talking about radius of that puddle and area of that puddle, that's really important too. Let's think this through. First off, the faucet is, water is streaming out of the faucet at this rate. That's telling me something about how the volume of this puddle is growing. Hopefully that makes sense, that if water is going into it, then the volume of the puddle is growing at a rate of 2 cubic inches per second. All right. That's how the volume is going. So we need to start out thinking about the formula for the volume of a circular puddle. Now, the volume of a puddle, this puddle is circular with a depth of 1/8 inch. That means this is the volume of a cylinder, a very shallow cylinder, but it's still a cylinder. So circular, we're going to go pi r squared times the depth or the height of the puddle. In our case, the height is going to be a constant 1/8 of an inch. So I'm going to put that 1/8 in front here. That is the volume of the puddle at any given radius. Now, we want to examine how the rate of change works. We're going to take the derivative of each side with respect to time. On the left-hand side of this equation, the derivative of the volume with respect to time just becomes dv over dt. Because this variable r is inside a squaring component, I have to take that 2 out front, which gives me a 1/4. So that's just 2 times 1/8, multiplied by pi r to the first power. And then I can multiply times the derivative of my inside function with respect to t. So I take the derivative and then I have to multiply times the derivative of the inside function. It's at this point we're going to look back and say, well, the volume that the puddle is being increased by is at a rate of 2 cubic inches per second. That's the dv over dt. That is equal to 1/4 multiplied times pi r times the rate of change of the radius. The rate of change of the radius can be found at any given r using this formula. I would just plug in r and solve for dr dt. Let's go ahead and solve this to make it easier on ourselves. Essentially, I'm going to multiply both sides by 4 and then divide by pi times the radius. And then that is going to be the change in radius with respect to time. Our problem asked us to find the change in radius with respect to time, both initially and when the radius was 10. Let's start where the radius is 10. If the radius is 10, all I have to do is plug in the 10 into my formula. So pi multiplied times 10 becomes the denominator. I'm going to write that as 10 times pi. And that's your change in radius with respect to time. If you want to look and calculate the change in radius with respect to time, or when the radius is at 10, then what you can do is you can recalculate this, and this is approximately 0.2546. So this situation says if the puddle had a radius of 10 inches and water was flowing in it, then the radius of that puddle is growing at about 0.2546 inches per second. You can trace back how I got inches per second by doing this. Remember, the 2 was inches cubed per second, and then the 1/4 came from a 1/8 inch depth, and the radius would have also been in inches. So about 0.2546. So if water is flowing into this puddle, then the radius of that water is growing at a rate of about 1/4 of an inch per second. Let's talk about initially. Well, initially would be when the radius is 0. So when the radius was 10, we had no problems with this formula. However, you'll notice that when the radius is 0, we have some problems with this formula because we don't want to have to divide by 0. You could take a limit as the radius gets closer to 0, and what you would find is you would get a limit which forces this thing to be infinite. That means that the radius is changing at, an infinite speed, because if you think about it, it's going from 0 to anything is an infinite percentage change, if that makes sense. So it's initially the r equals 0 does not work very well. For that reason, we try to avoid using the initial time the initial radius of 0 in our calculations. All right. Now, the other thing it said to do, we found the change in radius with respect to time in both these cases. We're going to say this one just does not exist. Some people would say infinite. That's okay. So initially, it doesn't exist or it's infinite would be fine. But we were also tasked with finding what is the area? How is the area changing when we're putting in 2 cubic inches per second of water? You can do this one of two ways. The first way is to utilize the change in our radius to compute a change in the area. We've done that in the previous example. We looked at how the area of the circle changes with respect to the radius. And we found out that the change in the area of a circle with respect to time was 2 pi r times dr over dt. So if I wanted to look at the change of area when the radius is 10, what I can do is say the change in area with respect to t is 2 times pi times r. R in this case is 10 times the change in r with respect to t. The change in r with respect to t is this, 8 over 10 pi. And then simply calculate that. The pi's are going to cancel. 2 pi times 10 is 20 pi times 8 divided by 10 pi. We get, I believe, 16 as our final answer. So if the puddle is receiving 2 cubic inches per second, then the area of the puddle is changing at a rate of 16 square inches per second when the radius is at 10. If the radius was initial, obviously we can't do that because we have a 0 there. So this is option 1, is just to, now that we've found the rate of change of the radius, we can connect that with the rate of change of the area. Option 2 would have been noticing that in this initial volume calculation, we had volume equals pi r squared times h. That pi r squared is actually just the area of the circle. So the volume can also have been written as the area of the circle times h. If I want to view our particular circle, remember our particular circle had a depth of 1/8. I should say our particular puddle had a depth of 1/8. And so the volume of that puddle would be area multiplied times 1/8. And then I could have taken a derivative of this, derivative with respect to time equals 1/8 multiplied times derivative of the area with respect to time. And what we said was that the change in volume with respect to time was 2 cubic inches per second. And the change in area was the thing we were trying to find. The change in area with respect to time was the thing we were going to find. So if I multiply both sides by 8, I also would have gotten 16 is equal to the change in area with respect to time. So if the volume of the puddle is changing by 2, then the area of that top surface of the puddle is changing by 16. And that, once again, is square inches per second. Hopefully that makes sense. Either way is fine. However, as you notice, we're going to also avoid the initial condition of 0 again. If you talked about the area of that puddle or the volume of that puddle, we're getting ugly stuff there. So hopefully that makes sense. By the way, it's not so difficult to talk about initially here or at any radius. So the area is always increasing by 16 square inches per second. But that means different things with respect to the radius. When the radius is big, adding 16 inches per second to 16 square inches per second to the volume doesn't increase the radius very much. But when the radius is really, really tiny, adding 16 square inches per second to the area increases the radius by enormous amounts. So if I start with a circle of radius 2, let's say, and I want to increase it by 16 square inches, the area by 16 square inches, I might have to really, really increase the radius by a lot. But if I start with a circle of radius, let's say 10, if I want to increase the area of that circle by 16 square inches, I might only have to go up just a little bit because it just covers a lot more distance. So that's kind of what's happening there. That if you want to increase the area by 16 square inches, if we start with a small circle, that means we have to increase the radius by a lot. But if I start with a big circle, I might have to increase the radius by just a little bit to get up to that 16 square inches. So the area is always increasing by that 16 square inches. And in fact, this would be the case when R was 0 and when R was 10, because this is independent of my R. But in terms of the radius growth has to grow tremendously when my radius is really, really small. But when my radius is bigger, we don't have to grow that much. I would like you to calculate one of these on your own. So push pause on the video and try this problem. How fast is the radius increasing when the radius is 1 centimeter, 10 centimeters, and 50 centimeters? This problem is about a circular balloon. So think sphere, and it's inflated with air at a rate of 5 cubic centimeters per second. So think volume of a sphere. If you don't know that, you can look it up and try doing this problem with these three numbers.